Hello everybody, this lesson is going to be about Raoult's law. This is going to allow us to do some calculations involving vapor pressure. So we've already learned about what vapor pressure is, but now we're going to look at some of the calculations. So when we have a non-volatile solute inside your solution, it's going to lower the vapor pressure of the solvent. So if we have a solvent like water, there's a certain amount of particles that are in the gas phase at the top of the container, has a certain vapor pressure. If I add, say, salt to it, the addition of that solute is going to result in not as many water particles being in the gas phase. And so the vapor pressure in the container will be lower than if you only had water. So this equation has the pressure of our solution, that vapor pressure. It's going to have mole fraction of solvent. And then P0 solvent is whatever the vapor pressure of the solvent if it was just by itself, if it was the pure solvent, pure water, for example. We call this vapor pressure lowering. So the vapor pressure of your mixture, of your solution, when you have that non-volatile addition, is going to end up lower than if it was pure. We saw it's directly proportional to the amount of solvent. And so the lowering, the vapor pressure lowering, is just the subtraction. So our delta P is the pure solvent minus whatever the pressure is when you have the mixture. So you can do a variety of calculations using these equations. So let's think about why this occurs. We've learned that there's a dynamic equilibrium, right? Throwback to the equilibrium chapter. There's an equilibrium between the liquid phase and the gas phase. Some of the particles are vaporizing at the same rate that some are condensing back into the liquid phase. So what ends up happening is that when you add your solute, when you dump in, for example, your salt, some of the surface area is taken up by these solute particles, which means that there's not as much surface area exposed for the solvent to vaporize. You will end up with a new equilibrium. You'll get to the point again where the rate of vaporization and the rate of condensation is the same, but it'll be lower because those solute particles are in the way, aren't they? So I don't know if you can kind of look at this picture and see everywhere where there's one of these red circles up at the top is a place where a water molecule cannot escape, right? Those little red circles are causing the problem. So eventually, yes, you'll get to a new equilibrium, but you're not going to have as many vapor particles up here. They did not have the opportunity like they did when it was just the solvent. Now, if you look at this picture, do you notice how there are none of those red balls up in the gas phase? That's because it's non-volatile. The solute does not turn into a gas there. It stays in the liquid phase. Unfortunately, that's not always the case. Sometimes you may have a solution where both substances are volatile. Both of them will be in the gas phase a little bit. So you may need a slightly different version of our equations here. We call it modified. When you have non-ideal interaction, that means both things are volatile. They both want to vaporize a little bit. So what you will have to do is take into account the mole fraction, how much is coming from A and how much is coming from B. This vaporizes a little bit and so does this one. This is right back into the gas chapter, isn't it? You gotta think about the pressures there, those partial pressures. Do you remember Dalton's law of partial pressures that we learned about in the gas chapter? It's coming back in the solution chapter, isn't it? So an ideal perfect solution, kind of like we had ideal gases, right? This ideal solution would be one that follows Raoult's law. Not everything is perfect. If you have what's called a negative deviation, that means you're going to have a lower vapor pressure than you expected. Not as many particles will be in the gas phase. This can happen when your solute and solvent are very similar, when you have strong forces of attraction between them. They will hold each other down in that liquid phase. It will take more energy to vaporize. They would prefer to stay a mixture as a liquid in that solution. A positive deviation is when you're going to have a higher vapor pressure than you expected. More particles will be in the gas phase than you anticipated. That can happen when there's really not a lot of attraction between those solutes and solvents. It's going to be super easy to vaporize because they don't care about each other. They don't need to be held together down in the solution. They will happily go up into the vapor. So you can look at things like the polarity to kind of guess what will happen to the vapor pressure. So thinking about this some more, right? Your ideal solution is when the interactions between the solute and solvent are the same as breaking your solute and your solvent interactions between each other, right? So you end up with a situation where it behaves perfect. It's all equaled out. And then if you're in a situation where the solute-solvent interactions are either stronger, they prefer each other, or they're weaker than what the sum would have been, then it's not ideal. Either a positive or a negative deviation. I'm just trying to show you slightly different phrasing of the exact same thing. I have found over the years, one of these slides tends to click with everybody, but which one depends on who you are. My personal preference is the next slide. I like the graph version. When I see the graph, to me, it makes more sense. So let's look at these graphs for the possibilities here. At first, these graphs look bonkers. There's so many lines, and now we have dotted lines, and why are some bending, and it can be a little overwhelming. So always look at your axes first. if you notice, we have vapor pressure here, increasing as we go up, and we have mole fraction on the bottom. A is our solute. So it's how much solute have I dumped in compared to just having the pure solvent. If I don't have any solute, I'm down here at 0, which means my vapor pressure would be the pressure of the pure solvent. And then as I add more solute, look what happens to the purple line. The purple line decreases. The vapor pressure lowers as my red line increases. That's perfect. That's exactly what Raoult's law says should happen. Oops, I got a spelling mistake. Hold on. All right, that's better. Okay, now let's look at the next graph. Here we see as I increase the amount of solute, my vapor pressure decreases, but whoa, it decreases a lot more, doesn't it? I have way less vapor pressure than the dotted line would anticipate. Because the solute and the solvent love each other. They do not want to be vaporized. They want to stay next to each other, attracted to each other, strong attractions holding them in that liquid phase, preventing them from going into the vapor because you would need way more energy to pull those good, strong attractions apart. Now let's look at the last graph. As I increase my red line, oh my gosh, look, it is decreasing, right? But it's way more than the dotted line says it should be. That's because the solute and the solvent do not care about each other. They're like, get me out of here, I'd rather be vaporized. They would much rather be a vapor than be near each other in that solution. So I know we don't often encourage personifying things, but I even though you wouldn't write a personified answer on your FRQ, I think it helps to explain what's happening here. Your brain can kind of process it. They don't want to be in the vapor because they're really attracted to each other. They like each other. Here, they are not attracted to each other. They are trying to escape into the vapor. This is called a negative deviation because it's lower than expected. This is a positive deviation because it's higher than expected. All right, everybody, that was it. I hope that was helpful. Bye.